Today we're going to be looking at emission spectra of atoms. Yesterday I looked at thermal radiation, which is something that's produced when you have either a solid or a dense gas, or you could even have it from liquid, I guess, but usually it's a dense gas when we're talking about thermal radiation spectra. And it's where there's a lot of interaction going on between the different atoms all the time. And so the light that they produce is sort of a product of all of the atoms in a way at the same time and in a big group. Although when you get it down to it, it's actually individual things going on, but there's a whole bunch of interaction. Today, we're going to look at something called emission spectra of atoms. And this is where the atoms by themselves are giving off light, and they're not interacting a lot with other atoms while they're doing it. So they're kind of independent in a way. So how do you get an atom to emit light all by itself? First of all, you have to get the atom, what we call excited. And what that means is you could put it in a strong electric field. At school, we have some power supplies that we can do this with. It's got a little glass tube with an electrode at each end, and you connect it up to a 5,000 volt power supply, which makes a fairly strong electric field. And the atoms get excited when that's the case, and they give off light. Or you can get a rarefied low density gas, very hot, where the atoms will have a collision. That collision will get a single atom or maybe a pair of them excited, but then they don't have a lot of interaction before they give off the light. And then you can study the light from the atoms using either a prism or a diffraction grating. There's lots of different ways that you can do it. Now, this picture shows something that you can see there. And up at the very top, there's a nice rainbow colored band. That would be a continuous spectrum. That's what you'd get from a solid or a very dense gas. The next one down is, you can see the word hydrogen here. This is the spectrum that hydrogen by itself would emit. These don't quite do it justice. They've got a lot of blurriness to them. But if you just had hydrogen in a tube, you'd get a bright red band, and these colors aren't quite right. And then you get a kind of a turquoise band over here, and then a violet band over here. And these are okay. They're kind of illustrating the idea a bit. If you had helium instead, you'd also get a bright red band, but not exactly the same color as that for hydrogen. You get one in here that we actually had helium, and we can do this in the classroom. I've got the setup for it, but it just doesn't look the same as here. Anyway, if you did it with helium, you'd see kind of a peach colored is what this one's supposed to be, and then some greenish things and some more turquoise stuff and some other violet lines. But none of these colors that you'd see in helium match up exactly with the colors that you see in hydrogen. And if you measured their wavelengths carefully, you'd find out that they were different. Similarly, you could take some argon. Argon is one of the common elements in Earth's atmosphere, actually. After nitrogen and oxygen, argon's the most common. And it has its own set of colors. Then you have nitrogen down here. And this ends up looking a lot different than the other ones above it, primarily because nitrogen forms a molecule. Two nitrogen atoms will form what we call a diatomic molecule, and those have different sorts of spectra. In fact, if you carefully studied the hydrogen, the helium, the argon, these vertical bands of color that you see, which are actually caused by the instrument that you use to see it, the vertical bands are, but they're extremely narrow. And that's not the case when you have a molecule like nitrogen. It ends up being kind of spread out. And these all look like they're kind of defocused, maybe just to give it some width in the picture. Then neon. Neon has a lot of bright reds and yellows and oranges in its spectrum. And when you mix them all together, you actually see the neon light color, which is a bright red light. Mercury, kind of dingier colors in Mercury. There don't have any reds in that, but have a lot down toward the lower end of the numbers for the spectrum here. And then carbon monoxide, that's another molecule, and you can see it's kind of a continuous spectrum on here too. So that's what you see when you look at those. So what's going on? Why is it that atoms of every different element give off entirely unique sets of colors? And why is it, and this is something I didn't mention, but it is true, measuring the wavelength of a single one of these colors accurately, and you can measure these extremely accurately, will instantly determine the element that produced the color. And I've got a book in the classroom called The Handbook of Chemistry and Physics. It has 120 pages of fine print data, 4 columns on each page, of the wavelengths of light given off by the elements. 120 fine print pages on there. And it goes from actinium to zirconium. That's the A to Z of the elements. And you have all of the elements in there. Nowadays, you wouldn't use a book. It'd all be in a computerized database. But still, there's a whole lot of data. And understanding what was going on with this was the big challenge in the early 20th century. At the start of the 20th century, most scientists thought that there was probably something called atoms, tiny particles of stuff. Not everybody, though. There was actually a significant proportion who did not think there was such a thing as atoms. But most scientists thought that there were things called atoms, but they didn't know a thing about them. Late in the 1800s, the last part of the 19th century, the British scientist Thomson first discovered that you could pull little negative charges out of atoms. We now call those things electrons. In those days, they called them cathode rays. But he discovered that electrons could come out of atoms, but they didn't know anything else about the atoms. However, they knew they were neutral most of the time. So if you pull an negative electric charge out of it, there must be some positive charge in there to balance that out. So we'll start off by just having a general introduction to atoms, and then we'll move on from there. So here's some general background about atoms. One thing about them, they have a tiny positive nucleus. And this may be old hat to you, but that's okay. Tiny positive nucleus with protons and neutrons. And second thing, the nucleus is surrounded by electrons. Now, in the early part of the 20th century, the first assumption was that they didn't know there was a nucleus, for one thing. All they knew was that atoms had electrons, but they were neutral most of the time, the atom was, and so there must be some positive charge. So at first they thought that the atom was this ball of positive charge, and it had a whole bunch of negative electrons embedded in it that balanced out the charge somehow. They did some experiments. Ernest Rutherford is someone who's well known for discovering the nucleus of the atom in one experiment. After discovering the nucleus, then the assumption that they made at first was that the electrons must orbit the nucleus just like the planets orbit the sun. And that's still the model of the atom that most people carry around in their heads, but it turns out it's not correct. The electrons in the atom act much weirder than orbiting planets do. Planets stay on their orbits nicely. Electrons, you can't pin down to a certain location in space. And so we're not even going to try to understand what the atom must look like, because the picture that virtually everybody carries around with them is one that has things that look like this that are supposed to represent the orbits of electrons. And the language that we have in science still uses the word orbit once in a while. If you take a chemistry class, you may have learned about orbitals. Forget about orbits. Just don't even try to picture what's going on in the atom. However, scientists did figure out that electrons have specific energies in the atom, and understanding those specific energies is the key to understanding what those spectra that we saw are and what the spectra of atoms happen to be. So here's a better way to picture an atom. So forget about that. And I'm going to put picture in quotation marks. If we actually tried to see an atom, we'd have to shine light on it, and we'd find that the very act of shining the light on the atom will end up messing up the picture that you see. So it's pretty strange anyway. But what we'll do is I'll just draw an oval for the atom, and the oval isn't necessary, but it's just some place to put what else I'm going to draw. And then inside that oval, I draw a bunch of horizontal lines. And usually I don't draw this many horizontal lines. It's just the atom, and it's just a way of containing my horizontal lines. The horizontal lines represent energies of the electrons. And let's see, I should say possible energies of the electrons, from low, and that's at the bottom, to high at the top. Now, something that they found out in the early 20th century, and by the mid-2020s, they pretty much had this stuff all figured out, was that the electrons are confined to particular energies, and they can't have energies between these things. And so if we think of this as being the zero level down here at the bottom, then they might have this much energy or this much, but in a particular atom, who knows what this one might represent, they will never have an energy halfway between or partway between any of these levels. They're locked into those levels. And that's what they learned about atoms. And so instead of trying to imagine some picture like this, which is absolutely incorrect, a better way to think of it is that you just have these energy levels for the electrons. They're what matter, and they're what produce observable results, whereas this other picture doesn't. Anyway, these energy levels will kind of let us understand what's going on. And here's what happens when you put an atom in a strong electric field. You may have had an electron down here at the bottom before you stuck it in the electric field in the lowest energy level. If you give energy to that atom, whether by putting it in a strong electric field or it collides with another atom or something happens, that electron can jump up to a higher level. It'll absorb the energy of the collision or from the electric field or something, and then the electron will be gone from here and it'll be up here. So that would be an excited atom because the electron is not in its lowest energy level. Then that electron can fall to a lower energy level, and it isn't necessarily a physical displacement in this case. It's just the electron is in a particular state, a way of behaving when it's up here, and then it will lose some energy and it'll be in a new way of behaving. And so just kind of flops down here. Maybe it could fall one level or two or three or four or five or all the way to the bottom. It can do lots of different transitions. But let's just suppose it drops down here. it loses energy. So when an electron falls to a lower energy, or I'm just going to say changes to a lower energy level. So when it changes to a lower energy level, the energy it loses is carried away as light. And that's how an atom, a single atom, emits light. If you took a bunch of atoms and kind of strung them out next to each other, that would be really hard to do because they don't sit still. But if you could string them out next to each other, it would take about 100 million atoms to get from one side of my little finger to the opposite side. And so they are tiny. And then if you wanted to fill the tip of my little finger with atoms, or if you had something that was that volume, you'd have 100 million atoms one way by 100 million by 100 million the third dimension. You'd have 10 to the 24th atoms there, which is a million, billion, billion atoms in a little container the size of the tip of your little finger. They're tiny. And you rarely have just one atom that's giving off light. If you've got a sample of some material, like a sample of hydrogen gas or helium or argon or any other gas, you're going to have a whole bunch of atoms in there. And you don't just excite one atom in it, you excite a whole bunch of them. And so you may have quite a few of those atoms that are doing this particular transition. They'll produce a whole bunch of light of that color or that energy. Other atoms might be making a transition here. Other ones might be making this transition or this transition. And when you've got 10 to the 20 something atoms in your sample, you're going to get a whole bunch of light of every different possibility coming out of this thing. And that's what we call the spectrum of the atom. It'll be the set of individual colors that atom happens to give off. So some things about, a little bit about the math of this. We're not going to plug numbers into this just yet. We'll still express the mathematics. Some of this was developed by Albert Einstein. He actually got his Nobel Prize for explanation of the energy packets that are carried away by atoms. And the word that he used for the energy bundles, the little individual particles of light, are photons. Actually, he didn't use that word, but shortly after he came out with this hypothesis, he called them light quanta. Someone else called them photons, and that name has stuck and we still use it. And if you were a Star Trek fan of Star Trek The Next Generation, or actually I think in every Star Trek movie since, they talk about photon torpedoes, whatever those are. I don't quite understand them. But anyway, Einstein's photons. Einstein said that a photon would have an energy, a bundle of light, which is a constant that we call Planck's constant. It's just denoted by the letter H. And we divide it by, we multiply it by the speed of light. So the numerator of this fraction is just a couple of constants multiplied together, and we divide it by the wavelength of the light. So something that this means is that the longer the wavelength of the light that's going to be, that means you'll be dividing a constant, the stuff in the numerator, by the wavelength of the light. The longer the wavelength, the less energy the photon will have, or the shorter the wavelength, the more energy the photon will have. And that's important. So long wavelength, a long wavelength is low energy, a short wavelength is high energy. So the other day when we first had our introduction to light, long wavelengths were things like radio waves and microwaves. Those are long wavelengths for light, at least. Those are low energy photons. Short wavelengths were things like X-rays and gamma rays. Those are the things with high energy. Okay? Ultraviolet has a much shorter wavelength than visible light. or somewhat shorter wavelength than visible light. It's got more energy than visible light. Visible light generally doesn't have enough energy to ionize atoms, but ultraviolet light does. X-ray does for sure, and gamma rays can have so much energy they could ionize, which means to knock electrons loose from a whole bunch of different atoms before they'd run out of steam. So that's something that happens. And Einstein and people who were working on this problem at the same time, like Niels Bohr and Werner Heisenberg and Erwin Schrödinger and lots of famous scientists that you may not have ever heard of if you haven't studied this before, but they worked on the problem and they zeroed in on understanding just how atoms emit light. And so it takes a whole bunch of atoms to give off a spectrum, but that's the way that we now understand it. By the way, for talking about the energy of these things, we haven't really used units of energy before, but an energy unit that's useful here is called an electron volt. And the abbreviation for it is just a, let's see, I think we use a lowercase e and a capital E for some reason. Anyway, EV is the abbreviation, and it's a handy energy unit for this. So, all right, well, let's see just where some of this math would lead us. By the way, the constant h times c, those two things multiply together. C is the speed of light, by the way. This Einstein's formula can also be written as E equals h times the frequency. But because the frequency of light is c over lambda, if you replace the f with c over lambda, then you get to this formula. And we mostly use this formula for photon energy in this class. So hc is equal to 1,240 electron volt nanometers. And we can calculate the range of photon energies for visible light. So let's do that. Okay, well, down at the long end of wavelengths for visible light is 700 nanometers, approximately. And that's the red end of the visible spectrum. The energy of those red photons, E, is going to equal hc over lambda, which in this case will be 1,240 electron volt nanometers. And we divide by the 700 nanometers, and we get whatever you get. I think it's around 1.77, but I'll check to be sure. Yeah, I get 177.
Me too.
Electron volts. So that's the photon energy for red light. At the other end of the visible spectrum is lambda equals 400 nanometers, and these numbers are just approximate, the 400 and 700, but we'll go ahead and treat them as if they were pretty solid. That's the violet end of the spectrum. The energy for that one is going to be hc over lambda again, 1,240 electron volt nanometers divided by 400 nanometers. Then I think we get 3.1. Yep, so 3.1 electron volts for that. Whoops, there's supposed to be a point on this one. So if you see visible light, that light has photons that are 1.77 electron volts to 3.1 electron volts. By the way, this idea of Einstein's that light carried energy as particles actually went against, about when he wrote it was 1905. it went against about 105 years worth of experimental observations that had confirmed that light behaves as a wave. And Einstein comes out and says, well, it acts like a little particle when it's emitted, or when it's absorbed, for that matter. And it was considered pretty controversial, and he didn't get his Nobel Prize for this work until, let's see, about 17 or 18 years after he'd written the paper on it. It was pretty controversial for a while, but even then, even when he was saying that it behaved as a particle, he still used the wavelength or the frequency when he was calculating the energy of it. And so he said, these are different kinds of particles. They are particles that still have a wave-like nature. And so he's kind of mixing this particle and wave idea. And you may have heard of that. It's not something we need to worry about in our class. All we care about is that we're going to have an explanation for the spectra of atoms. And so now we've got it. What happens in atoms of different types is that they'll have a different set of energy levels. The energy levels are determined, one, by the number of protons in the nucleus, and that varies from element to element. Hydrogen has 1 proton, helium has 2, lithium has 3, and so forth. And then there will be interactions between the most energetic electron and those that have less energy that just kind of stay put in their energy levels. And it's a complex picture. The mathematics of it is not fun. I got to mess around with that in graduate school. A lot of the work in understanding this was kind of pushed down the road a ways. They had a nice picture of it, but it was very tedious to calculate these energy levels until we started getting computers that can do nice repetitious calculations again and again and again. And if you program them correctly, they don't make mistakes. And so a lot of the work waited until we had good computer systems to do some of this stuff. But as far as tabulating the wavelengths that each atom gave off, they were able to do that long before we had computers. They were pretty good at designing instruments to do it. Now, the reason this matters is when we look out into space, we can see light being given off by clouds of matter, and we can measure the wavelengths of the individual parts of the spectrum that cloud will produce. And every time we measure a wavelength, we can say, oh, that's a wavelength for hydrogen. There's hydrogen in that cloud. Or that's a wavelength for titanium or something like that. A few years ago, there was someone discovered something orbiting the Earth. And as far as we know, we have just one natural satellite, and that's the moon. But every once in a while, well, in fact, right now, I think the Earth has captured a really tiny asteroid. And this is something that's just a few feet in diameter. So it's not like it's a big deal or anything, but it's interesting when we do capture something. But anyway, several years ago, they found something orbiting the Earth. So I thought, maybe we've got a natural satellite that we don't know about. But then they started studying the light from it. And this would just be reflected sunlight in this case. Sometimes reflected light will also carry the same information about the chemical elements. And they found out that the spectrum they saw was for titanium oxide. And titanium oxide, okay, so whatever this thing was that was orbiting us, it seemed to be coated in titanium oxide. Titanium oxide is used on Earth in white paint. And where this stuff, it's also used in clown white, or if you've ever used the super duper sunblock that just looks like white clown grease, and you might use that if you're mountain climbing on a glacier or something like that. Protects you pretty well. But anyway, NASA had used that stuff to paint the rockets that carried the Apollo astronauts to the moon. And what this was one of the old rocket boosters still orbiting the Earth way out there in space somewhere, or, not that much farther than the moon. But that's what it turned out to be, was an old NASA rocket booster. But they could figure that out by looking at its spectrum there. When you're talking about the set of colors that are given off by something, we call that an emission spectrum. And an emission spectrum is going to look like a black background with a few bright colors in it. So that's what it looks like. So a few bright lines of different colors is what an emission spectrum looks like. And it's caused by usually a gas that's at a low enough pressure where the atoms in the gas get to give off light without being interfered with by their neighbors. So that's something that can happen. Anyway, lines of different colors. Now, we've already learned about an absorption, or excuse me, a continuous spectrum, the thermal radiation spectrum. That's where you have a dense gas where when the atoms are giving off light, they are interfered with. And so with that, you get this continuous spectrum that depends on the temperature of the gas or the solid or whatever it is producing it. So that's another kind. And there's a third type of spectrum that we want to learn about here.
So the emission spectrum has nothing to do with heat then, like the thermal one does?
Not really, although if you have a low density gas and you heat it up, it will give off an emission spectrum.
Okay.
And it does have something to do with heat in that some of the transitions that the electrons make will only occur if the collisions are violent enough to bump the electron up that high.
Gotcha.
And that's something that does increase with heat. So, but you have to go to more work to figure out the temperature from an emission spectrum. And we will talk about that when we get to stars, because it plays a role there. However, I wanted to talk about something that happens with atoms. If you have an atom here that has a few particular energy levels, and I'll just kind of draw a bunch of them there, and let's suppose that the electron, the outermost electron on it, that is the one that usually takes place in these things, is sitting down in its bottom level. So it's at the lowest energy level it can be in. This atom can absorb energy, but only if the energy coming by, the light coming by, has exactly the energy of one of these transitions. So I'll write that idea down. It's really important for the way this happens. Atoms absorb light only when its energy is exactly right to bump an electron to a higher level. So let's imagine that a photon comes by this atom and it's only got enough energy to get the electron halfway up to that next level. That photon would just be ignored. It would just go right by the atom and maybe go on and interfere with some other atom or something like that, but it would not be absorbed by this atom. If a photon comes by that has an energy that places it partway between a couple of these bands, it's still not going to be absorbed. It's not like the electron would take some of the energy from it and let the rest of it go. It can't do that. It can only absorb just the right amounts of energy. And so one that's too energetic will also be ignored, unless the one that comes by is so energetic that it could liberate the electron from the atom. That one might be absorbed, and then the electron would leave the atom. But it has to be just right to get to one of these things. Well, it turns out that the electrons that, or the photons that could be absorbed to bump the electron up are exactly the same color and energy, same wavelength and energy of the photons that this particular atom would produce. And so what happens is atoms absorb exactly the same wavelengths of light they emit. Up at the top here, under the words continuous spectrum, you see the complete rainbow. Under that, you see emission spectrum. You see a dark background and individual colors. And then beneath that, you see absorption spectrum. That's what happens when you have a bunch of atoms that are absorbing the very same wavelengths they would emit. And I'll talk tomorrow or maybe later today about how you actually produce an absorption spectrum. But it can tell you the exact same information that an emission spectrum does because atoms absorb the same wavelengths they give off. And that's, I don't know what element these happen to be for, but a continuous spectrum, the thermal spectrum or black body, you have a hot, dense object like a very dense gas. That can give off thermal radiation at a whole bunch of wavelengths. The emission one is a hot, low density gas, and it's individual emission by each atom without interference from its neighbors for the most part. And the absorption spectrum happens when you have light from a continuous spectrum that passes through a cool, lower temperature gas. And then you get certain wavelengths absorbed. And for the ultimate in an absorption spectrum, there's this one. This is the visible absorption spectrum of our own sun. And it's just insane. And it starts way down here at the bottom left. And you have this continuous stripe moving across with a bunch of lines in it. And then you go up to the next row of color above it and keep going across. Several years ago, actually it's been more than 20 years ago now, but my wife and I happened to be in the Southwest for a week. I was going to a meeting, and we spent a week traveling around, kind of visiting observatories in Arizona and New Mexico before we went to this meeting. And we were up on Kitt Peak outside of Tucson, Arizona one day, and there's a bunch of telescopes up there. And we were just hadn't made any arrangements ahead of time or anything. We were just walking around enjoying the views and looking at these different telescopes. And this tour group came by, led by a guide. And I don't know how we got to talking, but he found out I taught astronomy. Then he said, "Whoa, come along with us." And there's a solar telescope on top of Kitt Peak. And they took us down into the basement below this thing. It has a big mirror that they reflect the light down to a reflection grating. That's one where it separates the light into colors from a mirrored surface. And when you're actually looking at the light that it studies, you have to have these big dark goggles on because it's so bright. But that's one of those places. And they take the visible spectrum of the sun and spread it out over this line of white table that's 90 feet long. It's kind of amazing. It was pretty cool to see, and just stumbled into it. But anyway, this is the absorption spectrum of the sun, and you see all kinds of different lines in here. Sometimes they'll make these black and white because as long as you're measuring the wavelengths of light, you don't really care much about what color it is. And this is a tiny part of the spectrum from the sun. It's from 530 to about 532 nanometers. Now that's out of the 400 to 700 part, so it's just two. The units that are on here are a little different. There's an A with a circle on top of it here in the middle. That's called an angstrom, and it is 10 to the minus 10th meters, where a nanometer is 10 to the minus 9th. And it's a unit that was used historically, and it's still used in astronomy quite a bit. And so, but if you just move the decimal point on these numbers over by one spot, so the 5,305, you'd call 530.5 nanometers instead. But looking along here, you can see what elements it is in the sun that produces the absorption line. So here's one Fe1, that'd be for iron. La, I think, is lanthanum, and that's lanthanum 2. Cr is chromium, chromium 2. Here's some more iron, and Roman numeral 1, chromium 2 again. The Roman numerals mean the state of the atom. If it's got a Roman numeral 1, then it's neutral iron. If it's got a Roman numeral 1 for chromium, it's neutral chromium, but the chromium with the Roman numeral 2 means that the chromium has lost an electron, and so it's singly ionized. And it's kind of unfortunate that the 1s are neutral and the 2s have lost a single electron, but people who study this can keep track of that pretty well. And there's various other things in here, but quite a bit of chromium in this part of the spectrum. And more iron. Okay, here's an Fe2. That would be ionized iron. So an iron atom that's lost an electron absorbs color right here. And then Sc, I can't remember, scandium, maybe, don't remember. Nd, that might be a neodymium, but I'm not positive. I'm not a chemist. Y is probably yttrium or ytterbium. I don't know, there's a whole bunch that are named after the same town in Sweden, and they took variations on the name. But just in this tiny little part of the solar spectrum, you get a whole bunch of different wavelengths of light absorbed off there. When astronomers were studying this stuff in the early part of the 20th century, they looked at all of these different absorption lines for iron and thought, the sun must be mostly made of iron. And so that's what they thought for a while. But was a woman named Cecilia Payne who had learned about quantum mechanics and found out that a little bit of iron has a whole bunch of absorption lines in the visible part of the spectrum, and a little bit of iron can absorb a whole bunch of different wavelengths of light, and that's what's going on in the sun. Turns out the sun is about 3/4 hydrogen and 1/4 helium with trace amounts of all these other things. And we don't even see any helium or hydrogen in this part of the spectrum. Okay, one other picture of this. This is another way. The picture above is kind of like what we were just looking at, where we saw those different absorption lines. But the trace that's down here is something that's produced by, you actually have some information about the intensity of the light in the trace, whereas in this one, it's kind of either black or white in there. But something that shows up in the trace is that every place there's a dark absorption line up here, there's a dip in the intensity of the light from the sun, which means the light isn't completely gone in this region. It's just at a lower intensity, and it's not all the way down to 0. So there are quite a few dips that show up in there. So either one of these things can be used. You study the light, you see where the dips are, measure the wavelength of the dip, and you can figure out what element produced that dip. Or you study a color band thing like this and do the same thing. See where there's a dark band, measure the wavelength of it, and you can figure out what element caused that as well. So now we've got more tools, and we're going to start combining these things together, but we'll wait a day for that, and we'll wait till tomorrow to get to that. This is pretty mind-boggling, and it's not gone into in a great detail in the book.